Okay, Token Drop, episode 10. And, what was interesting the other day, we were talking about, we had an episode on this actually, which is about agents. And I was thinking more about agents. We talked about agent governance. But, thinking about it more deeply, there's a lot of different aspects of agents in an enterprise. There's, performance aspects, there's reliability, a lot of different aspects. And maybe we can throw out start off a discussion today about talking about what are some of those broader aspects of agents in an enterprise. So, what's your view on that, Sajad?
Yeah, I mean, an agent is how intelligence is manifested for some business use, right? It's a wrapper around an LLM, for instance. And you may, in a business scenario, you might treat an agent like an office worker. So when you think of an office worker, you have certain expectations, right? One, they're knowledgeable, they're responsible, they're usually correct in the things they execute to get the job done, right? You can expect some correctness and um, accuracy guarantees there. They're timely, right? The expectation is that these are timely in a way that things keep moving in a business environment, right? So likewise, you should have similar expectations of agents, right? Of course, given who we are and what we do, we are focused on correctness, mitigation of hallucinations, and so on. But that's just one piece of the puzzle, right? You want the systems to be timely, right? When you ask a question or when you have multi-agent workflows, and the expectations are that these agents are talking to each other in machine time. But LLMs, right, the best throughput that we've seen is about hundreds of tokens per second. And now, of course, we're starting to see emergence of new hardware accelerators that can deliver higher speeds, but still that's not good enough. We're still talking about seconds and multi-second response times. So we talked about timeliness, then correctness. Then there's reliability. How will multiple agents work as a group, right? And it's similar to multiple workers in an office environment getting together and trying to get some work done. So in that environment, if you see a worker falling ill or having to take some emergency time off, then other workers will fill in and bridge those gaps. Likewise, if an agent were to fall asleep or to fail, uh, how do you complete those transactions, right? So how do you discover these kinds of failures? How do you work around those failures? Do you have distributed algorithm awareness, semantics of distributed systems, right? Which is correctness at scale in a distributed environment, tolerating all kinds of failures, failure error, then discovering errors, recovering from errors, all of those things at distributed databases like MongoDB, Cassandra, and others have been tackling for at least the better part of a decade, decade and a half. We need similar distributed algorithms and distributed computing capabilities as well. So, and then of course there is security. So there is security, there's timeliness, there's correctness, and the awareness that you're operating in a distributed environment with other agents. And therefore, we have to have all of these recovery, fault tolerance, distributed computing awareness. So those are at a macro level, I thought, capabilities one should be mindful of. Yeah.
Hmm. It sounds like it's almost like an agent operating system you need because in
Indeed.
PC you have applications, for example, that might get hung up. Happens less than it used to, but it still happens, and I go and kill it on my Mac.
You,
What
you couldn't
happens if
have,
that happens in an enterprise environment?
yeah, you couldn't have said that better. Indeed, the operating system is the right language. And we're starting to see, things moving in that direction. We've seen inferencing services like VLLM or SG9. They're assuming more and more of the capabilities that operating systems were expected, and not just expected to, they do deliver in the case of real-time business applications, business services. But then there's a bit of a gap that we need to bridge. The operating systems operate at timescales of nanoseconds, uh, microseconds, milliseconds. Anything longer than a few milliseconds is treated like an I/O workload. You dispatch it to some remote system, and that remote system, when it finishes the job, will interrupt you and tell you that the job is done. So it's really not a first-class computational service. It's an I/O offload. But out here, as you're performing computation and ML inferencing, LLM inferencing, is actually a compute job. It's not an I/O.
That's right.
Yeah. So if you're looking at a compute job, how do you accord it a first-class citizenship?
Mhm.
And when you give it that first-class citizenship, does it then become?
But what do you mean by first class? You mean it has access to all the rights and privileges that it needs to, or what do you mean by first class?
Yes, by first class, I mean um, you are part of the CPU memory complex and
Hmm.
the protocols there. You have cache coherency protocols, right? One CPU would know that a piece of data is not in its own cache, but it's sitting in some other CPU's cache.
Yeah.
So when you perform some operation on that piece of data, the underlying protocols know how to fetch it from the remote CPU's
Hmm.
L1 cache, for instance, right? But when you have an accelerator performing some processing, your CPU has no idea what data is being touched by the accelerator, nor the accelerator has any idea which of the data which is in the CPU cache is getting modified, right?
Sure.
So that cache coherence doesn't exist. So you really need, and people are working on it, right? Building CXL and various other experimenting with various other technologies and substrates for and protocols to make that happen. So that's just one aspect, right? If you want to be a first class citizen, I think you need to be treated on par with the CPU and the memory in that complex.
Yeah.
And need to be collaborating and cooperating and scheduling and executing
All right.
instructions. That's not happening today.
And these agents would seem to need memory just like an application, right? We were just talking about the other day. You have an agent that helps people order coffee, and you don't want to have the agent keep asking you, do you want cream and sugar? Because
Yeah.
people say, I told you the last 5 times, right?
Yes.
And so you need some mechanism in this operating system to enable the agents to have some sort of persistent memory.
Indeed, I think, and memory, as you know, we have as human beings, memory is structured into a hierarchical
Hmm?
memory tiers. There is short-term episodic memory, right? If I speak to you about something, you expect me to remember, right?
Yeah,
What I just said to you. But if you were to ask me 20 days from today, hey, we were discussing, did you order 1 cup of sugar or 2 cup? I mean, did you order 1 spoon of sugar or 2 spoons of sugar? I might not remember,
that's right.
right? So there is long-term memory, the short-term episodic memory, and and then there's session memory that's relevant only for a given session. So memory itself can be classified into tiers, into hierarchy. How do you organize that, right? I think one way I'm thinking it's the right way to do things is probably extend the graph. We're talking about storing all the data in the graph. Can you extend the graph into an action space where some of the transactional state is also stored in the graph, and then that state serves the needs of these agents as they transact with each
A
other.
multi-dimensional graph.
Yeah, it's a multidimensional graph in the action space. Yeah, so that's
Hmm.
that's one thought. We haven't really fleshed it out, but that's something to work on next time. So that's where I'll pause here. Let Sam maybe
Yeah,
answer.
Sam looks like he's got something to say here.
Yeah.
Yeah, actually, I think Sujad spoke spot on some of these points, actually. I just think that merely having agents doesn't really solve some of the problems that these agents are bringing to the table right now, actually. Like, for example, some of the things that Sujad was talking about specifically in terms of, the failure surface, right? I mean, now, what happens is basically you have a bot, say, and it makes a query, and then some data is returned. This could be structured or it could be unstructured. But eventually, what happens? There are two portions to that equation, where when the natural language question has been posed, it needs to be processed, and it must be built into a query, right? And that's one part. And the other is it goes and queries say the LLM queries the agents query the database, and when they return it, that return again has to be converted into prose. So there are two parts to the equation where failure could happen. And the reason is if this is not grounded on some source of truth, then probably the data that's returned would be incorrect. So if you do multiple calls and multiple agents respond to the same call, they would really return inconsistent data, right? I mean,
Are you
so
talking like a chain of agents? One guy gives,
yeah.
is that what you mean? One guy gives an answer to somebody else, the next agent, and those things the error rates
No, the
multiply
same
up.
agent itself, right? I
Mhm.
mean, suppose you query multiple times, because there is inherently this translation that's going on. If it's not grounded
Mhm.
on something like what we're talking about is which is mostly on an ontology-based system or basically unless it is verified, you do not the answer that you get for those queries may be inconsistent. So if you ask it multiple times, it might produce different answers. And this is very much possible, and we have seen this in agentic systems.
So you're
The
speaking of
second,
the correctness guarantees of
exactly, the correctness guarantee is very, very important. And the second thing that I also think is Sujat brought in excellent points, like the working and short-term memory. Like suppose you have a conversation going in, and every time you walk in, and the agent really says, "Who are you? I mean, what do you want?" You get irritated, right? I mean, actually, you wanted to preserve some kind of data, or you want the agent to have some memory. So next time when it comes in, it says, "Hey, Sam, how are you doing?" Right? That's better than really saying you got to start with everything from blank page, right? I mean, which is what most of the times we do these queries that happens actually. So what happens is there needs to be this notion of working or short-term memory. Along with that, we need long-term memory, which I put it as episodic, semantic, and procedural. And these memories also need to be there, right? I mean, so when you want to bridge all these things together, now it becomes a different ball game. So why is memory a first class reliability risk? Actually, there are many modes of poisoning that can happen. Actually, for example, there are at least three failure modes in memory where you can see. One is memory poisoning, which you can see. The second is stale context, which you can get. And third is cross agent contradiction. These things really set the game, actually. So it's not as simple and straightforward as saying, okay, I brought in a bunch of agents, I can just code them in Java, and they're going to work. The second thing, and also the other thing is the orchestration patterns. I think Sujat alluded earlier, there are many patterns, common name patterns like sequential, concurrent, handoff, group chats. Like, for example, we were talking about just one of them, then orchestrator led. So now what happens is all these patterns, right? They really also bring in a lot of stuff. Like that's where exactly Sajjad was also bringing a very important point where, normally if you work in systems, you know what the order of magnitude of a response is. Operating systems are built for a certain kind of response. But here you have these systems which take responses for in the order of seconds. So there is an impedance mismatch we're seeing here, right? So that is another point. So therefore, different patterns like
You're saying that
sequential.
operating systems today expect like, maybe millisecond, but this is, multi-second.
It's multi-second. There's an impedance mismatch. So now the question is, how do you, because we have had this problem forever, right? I mean, I worked in PaxOS, and we have different kinds of databases. Like for example, we had React, we had Cassandra. All these systems are eventual consistency, right? And they base themselves on the CAP theorem. Now the same problems would surface when we are seeing multi-agent scenarios. There are failures.
Mhm.
And then also in these things, you have transactional boundaries. So when you're talking about transaction, but what is that you're talking about? Right? Every layer does something. Now, what happens is in certain cases, each layer should be semantically correct, right? So you can really have transactional boundaries for them. But now what happens, you can have multiple smaller transactions and they can be like, grouped together into a bigger transaction, right? And what happens is when something fails, a portion of the transaction can be rolled back. Now, the question is, how do you do that in the case of agentic systems, right? How do you build these transactional boundaries? How do you bring this Uber guy, the Uber transaction, which maintains this? How does it tie the shoelaces together? This is not just an orchestration
Yeah.
problem. It goes
It's really interesting because I was talking to a friend the other day. They were calling an LLM via an API. They have some application, and he had set his timeout to be 30 seconds.
Yeah.
And based on his historical experience, 30 seconds is an eternity.
Yeah.
But he was seeing timeouts because of the fact that the LLM gets kind of busy. It was a popular LLM, gets busy, and sometimes took more than 30 seconds.
Exactly.
And so he had to adjust his window to be more just because of that. And
and that brings us into another question, right? It's a more profound question now. So should we treat these systems as computational systems, which means then you expect extremely low latency,
right.
Similar to how the CPU is processing data, right? Literally within clock cycles, you see something processed and stored in the registers, and those from the registers it moves to the you store it as you're processing it, you store it in registers, and then maybe from registers you push it out into memory, and then let somebody else consume it. Should we treat this as a compute surface, or should we treat this like a storage surface?
Right.
All I'm doing is I got some data, my machine is going to give me some information when I query it. It's like a passive database. So I send out a query and it gives me a response, and I'm treating it like a database. And if you treat it like a database, then timeframes of 1 second or multiple seconds are reasonably acceptable.
Correct.
You're saying because sorry, Sam, you're saying because the native, what I maybe called native compute that the agent is doing is very limited. It's passing off the compute to the LLM. Is that what you're saying? That's why it could be treated more as a database because it's not doing a lot of compute. It's doing a lot of data manipulation using LLMs.
What I'm saying, Sunil, is you can treat it either as a database, you offload a query and you wait for the system to get back with a response. It's a passive system that just gives you answers from what it has. Or you can treat it like a computational system that's really actively, dynamically working on real-time information flowing through you, right? If you have tick data, right? If you're a trader, a hedge fund trading on the New York Stock Exchange, milliseconds, microseconds matter for you, right? So the data is streaming in and you're processing it as and when it's streaming in, all that tick data that's coming in. So if that tick data needs to be processed in million microseconds. So, and clearly LLMs, if you want to use LLMs in those kinds of use cases, then there's miles to go to improve the performance and the integration of those kinds of systems into this low latency processing stacks, which means your processing system should be cache coherent with your memory, right? So you need cache coherent memory, shared cache coherent memory between the GPU and the CPU, right? So and those architectures, people are talking about it. There's nothing that's practically available today. Today, you still treat it like an offline database. You send some queries, it'll respond to you in its own sweet time. And if it's acceptable to your application, that's good enough. But if you want to participate in this real-time streaming signal data processing, then you want, another step up in performance and capabilities.
Correct. Actually, if you really look at it, there are two halves to this, right? What are the two halves? The orchestration pattern that determines who talks to whom, right? A talks to B, right? While the memory architecture determines what they each know and trust. two different things, actually, right? I mean, the orchestration pattern and the memory architecture, right? A multi-agent system with a great orchestration but unbound self-written memory, which is what Sajad was alluding to, will still drift. And when the drift happens, it will lead to a confident contradiction. This happens all the time in agentic system. The shared verifiable semantic layer is what keeps a sequential pipeline or a parallel fan out or an orchestrator led kind of swarm, right? All have them mean the same thing. And that is the verifiable thing, actually, which we were talking about earlier.
Yeah.
Without that, what happens is the orchestration pattern may be good, but the memory really gives you that it lands you in trouble, actually, because of the drift that you will see. And that's where we were talking about. Are we
I don't
going back to
understand. How does
distributed
drift
systems
and
design?
memory interact? You say that's unbounded memory and that it can.
Yeah. What's the drift you're referring to,
Yeah.
Sam? Sorry. Yeah.
So, so what I'm talking about is here is the different types of memory we have and how these agentic systems are communicating with each other. These agents communicate with each other, right? I mean, they might do a write back, and when they do write back, they are writing a system of record, actually. Now, if in case due to incorrect processing, if something is written and it's not correct, or it seems to drift from the actual facts, over time this drift will compound. We've seen this. This is the compounding of failures which we've seen in systems,
So
and
if you
naturally,
could,
what happens is that causes this causality, wherein ultimately you find that we have drifted all the way out from what the source.
it's a function of, look, if you have two agents working on some shared task, and they could be operating on their own states, and then of course you could have some drift if the uh, the tasks are not mediated effectively. But if they're working on some shared state, then you have a chance of deadlocks, live locks, and all kinds of race conditions. And even there, you have to orchestrate correctly for guaranteeing correctness of those transactions.
Correct.
So either you have shared state, which means you need to coordinate how they read and write, or you have distributed state. And in distributed state, you have again two cases. One is you don't care.
Yeah.
Right? You maintain your state, you do your job. All I care about is when I ask you a question, you got to give me the answer.
Answer.
But I'm not going to have and retain state about what I'm not going to duplicate the state that you're maintaining.
Correct.
In which case, again, there is no question of drift. But if I'm maintaining state and you are maintaining state, and yet I choose to ask you some questions, and you give me answers which differ from the state that I'm maintaining, then there is clearly some drift. And in that case, again, once again, you need correctness guarantees, sequencing. Regardless of what state or scenario you look at, you really need these distributed computing algorithms to coordinate these transactions effectively in a distributed environment. So you really need, like, you spoke about Paxos and Raft all the time, and like how distributed databases are designed, right? And in the most stringent case, you have a distributed lock manager. You assert a lock, then you write to a given location, then you release the lock. And then there are times when you hold the lock, you perform the transaction, then you die. And somebody has to discover that the lock is still held and then do a lock recovery. So, and these are not easy things. I mean, databases like Cassandra, Mongo, others, and Oracle RAC, they've all been solving for this for decades, at least a couple of decades now. So if you need those kinds of semantics, then it's a lot harder to do so. So I would argue, I think that we push it down into the database layer, and the agents can be treated more like applications, so they're a little less aware, but you still need to manage state and consistency in the database. So yeah, I think But all I was just saying is you cannot ignore that fact that this is shared state that needs to be
Exactly.
managed.
The shared verified semantic layer,
Yeah.
because of if you have different types of patterns like sequential pipeline followed by something which the DaaX might be built like that, right? Initially sequential, then they fan out, then they come back and combine. Now, when you have that kind of state, there is state being shared at certain levels actually. And that is what we have to be very careful with actually, because there are agents communicating. Like suppose you do an aggregation. Now the aggregation itself may be different agents bringing different states. And what if one of the agents doesn't really get back in time? Or what if one of the stuff that we got was incorrect actually? There are more problems. This is a typical problem which we face in everyday program, but this is much more in terms of the agentic surface.
Yeah. Yeah, that's true. So that's why I think, the systems have to be it's really critical to understand the business use case, how the business problem is decomposed into a technical solution, and then and what are the levels of abstractions that one can use and in the technical solution to making sure that if you don't want to own that responsibility, how do you delegate it down to the database layer and still deliver on the promise of correctness and guarantees? Yeah.
Correct.
I think we're out of time. So anything else, Sam? Anything else you want to end on?
That's pretty much we summarized it. So therefore, like any downstream agent, it needs to to verify against evidence, right, rather than inheriting some upstream guess. So that's where the real problem lies, and still the industry is trying to solve that actually in terms of the orchestration and the memory and things like that. But we'll eventually get there. But still, these are problems that we see in current agentic systems.
Yeah.
Great. Okay. Well, thank you guys. We'll talk to you later.
Thank you.